Hello, everyone. Thank you for logging in to Hamamatsu-sponsored webinar. We are going to spend the next 1 hour or so discussing light sources from UV to IR. My name is Slavomir Piatek. I'm a lecturer of physics at NJIT and also a science consultant at Hamamatsu, again, the sponsor of this webinar. The presentation is divided into 3 unequal parts. In the first one, we'll talk about some characteristics and definitions of light and light sources. This is not going to be an exhaustive discussion. I'm only going to focus on those characteristics that I will use in this presentation. The second part will be a discussion of a variety of light sources. The discussion will be rather high level. There won't be deep dives, though there's some technical information, especially from the physics point of view, will be discussed. Throughout the presentation, interspersed will be some advertisements for light sources offered by Hamamatsu. So let's begin with definitions and characteristics. Probably the most fundamental one is radiance. Suppose I have a source shown on the left. This source can be polychromatic, which means it may emit light with different wavelengths. The light emitted from a surface element in certain direction gives us a differential radiance, which will be in units of watts per unit area, that projected area, per unit solid angle, per nanometer. That nanometer is because, again, light can be polychromatic, and one can have different radiance at different wavelengths. If I integrate over the area of the source, then I'm going to get spectral radiance. If I were now to integrate over all the wavelengths that are present in the light, then I would have the total radiance, which will be now in units of power or joules per second. So this is how much light the source emits in all possible directions at all possible wavelengths. So here we are on the emission end. Somewhere, some distance away, there is an observer. So this observer is on the receiving end. And therefore, if I were to integrate light coming from all projected areas on the projected surface of the light source, I would get what we call irradiance. If we also integrate it over all the wavelengths, that will be total irradiance, which will be in units of watts per unit area, per meter squared, but that meter squared will be now the element of the receiving surface. On the other hand, if I want to know irradiance for a given wavelength, that will be spectral irradiance, and therefore we have per nanometer. Let's now go to the second, probably most fundamental description of a light source, which is its spectrum. So spectrum depicts simply composition of light, i.e. what wavelengths or frequencies are present. What we are going to learn in this slide is that there are a variety of ways of presenting spectrum. So on the left-hand side, we have spectral irradiance that we learned about before as a function of wavelength. I chose a source of light, which is probably not very realistic, but I wanted to make a point. It's one where spectral irradiance is constant with respect to the wavelength. However, please note that I can represent spectral irradiance in different units, like watts per meter squared per electron volt, and on the x-axis, instead of wavelengths, I could have photons energy. And the curve, the resulting curve, looks different. It no longer is horizontal curve, but it corresponds to exactly the same source of light. It's exactly the same spectrum. In the third depiction, I could plot spectral intensity in terms of photons per meter squared per nanometer versus wavelength, and we still have yet another shape of the curve. Before proceeding, I would like to point out that there are other depictions of spectrum depending on a group. For example, in spectroscopy, it is very common to represent wavelength in terms of inverse or wave number. Let's now discuss coherence. Coherence refers to a phase relationship in time. That's one. That's called temporal coherence. and in space. So that's spatial coherence. So let's look at temporal coherence. Suppose I am at some location in space and light is passing my location. I'm going to note phase of electromagnetic wave, let's say phase of the electric field. If there is a time interval where that phase relationship repeats itself, we would say that there is a temporal coherence to this light. What we see on this slide are wavefronts of a plane wave. I should point out that the plane wave has a perfect temporal coherence. There's a perfect phase relationship. However, if the light is polychromatic, that temporal coherence will be finite, and as we'll see later, it will depend on the bandwidth, which is effectively the spectral composition of the light. In case of spatial coherence, we are going to look at phase relationship at different points in space. So for example, for this plane wave, if I am positioned at 2 points on the wavefront, then those 2 points would be in spatial coherence. We can test coherence of light, both temporal and spatial coherence, with 2 well-known setups. Let's start with temporal coherence. Suppose I have a source of light and like to test how much temporal coherence the light has. I can send the light towards the classic Michelson-Morley interferometer with 2 mirrors initially at equal distance from the beam splitter. At the lowest point here, I observe interference pattern as a function of distance by which mirror M1 is moved. If there is a temporal coherence, then the interference pattern is going to change, alter. Incidentally, if I had perfectly monochromatic light, I could move the mirror even by infinite distance, and I would still see variation in the interference. However, if there is a finite coherence at some distance, the interference pattern variation will cease to exist, i.e. we've reached the limit of temporal coherence. So as said earlier, coherence time is proportional to inverse of the bandwidth, and therefore from this experiment we can determine that the coherence length, let's call it L sub c, is equal to 2 times d, which would be equal to c speed of light times the coherence time. Again, I note that for perfectly monochromatic light, the coherence length is effectively infinite. In case of spatial coherence, let's look at the following picture. I have some source of light, not spherical, some rough-looking source, and what's depicted are some wavefronts emanating from this source. Please note that the wavefronts are kind of rockets, depicting effectively, in this case, the shape of the source and the time of emission of the photons that make up these wavefronts. However, as the wavefronts propagate away from the source, they kind of become smoother. And so the coherence area, which we can see is approximately equal to the distance squared times lambda squared divided by size of the source squared, is going to increase because of increasing distance. So light becomes more spatially coherent as it moves away from the source. Please note something interesting is that if the source has 0 size, if S is equal to 0, then the spatial coherence area is equal to infinity. So point sources or pinholes, for example, will produce spatially coherent light. The degree of coherence, spatial coherence, can be tested with the classic Young's double slit experiment. If the light is coherent, you would have the interference pattern on the screen. However, if the wavefronts are jagged, incoherent, there will be no average interference pattern shown on the screen. Let's now discuss another property of light that is commonly of great use in practical situations, and that is polarization. So polarization refers to effectively direction of the electric field as the wave propagates. On this slide we see 2 extremes. One is unpolarized light. So I know you cannot see the mouse, so let me just describe. So the direction of light towards the upper left corner, where the arrows are pointing in random directions, that will be depicting unpolarized light. So there is no preferred direction in which electric field oscillates. The other extreme is polarized light linearly, where electric field oscillates as shown in the vertical direction. It is possible to convert one type of light, one type of polarization to another. For example, we can polarize light using the idea of Brewster angle, where polarization can be achieved by reflection from, for example, glass when the angle of incidence is equal to the Brewster angle. There are also polarizing filters which can accomplish the same. Let's now spend a little bit of time discussing some properties of pulses of light. So what you see here is, again, rather unrealistic depiction of pulses because they are square. Typically, in reality, you are going to have some Gaussian-looking pulses. But we can still make some points. So one characterization is peak power of the pulse, its duration, tau, and repetition period. If you take inverse of repetition period, that would give you repetition frequency. One can also define average power, which would equal to, in this case, for these square pulses, peak power times duration divided by repetition period. Peak power and average power are commonly used descriptors of light, especially from lasers. I should also mention that nature is not generous. There's always noise. And so let me mention, in this case, some noises that are potentially present. Jitter in the peak power, which means that not all pulses have the same peak power. There's some variation. And another possible jitter is in the repetition period. There are more jitters. You could have phase errors and others. But these are not discussed in this presentation yet. Another crucial characteristic of light source is its stability. In other words, how, for example, peak power or average power behaves as a function of time. We can talk about short-term stability on the order of actually even fractions of a second to long-term stability, which could be even on the order of hours, days, or even years. And so there's an entire universe of possible reasons why you could have variation on the short and long term. I'll mention few in the presentation. One important effect is the environmental conditions, for example, and importantly, temperature. Now, when a source of light emits light, that light can be manipulated, which means its properties can be changed. It can be focused, defocused, or its chromaticity can be changed. To do that, we use various devices, optical devices, and this slide is a summary, not exhaustive summary, of the devices. Mirrors, prism, gratings, filters, Bragg mirrors, MEMS mirrors, and others. So in what follows, I would like to discuss a few examples of shaping of light. And so in this example, we have some source, a polychromatic source, and I would like to achieve or create light that is coherent, collimated, and monochromatic. And by coherent, I mean spatially coherent. To do this, I could first let the light pass through the pinhole, and so that is going to produce a spatially coherent light, as we discussed earlier, since the pinhole here effectively becomes the source, and the size of the pinhole is small. That gives us large degree of spatial coherence. A collimating lens is the focal distance away from the point, from the pinhole, and that is going to collimate the light, and the filter then will make the light monochromatic. Please note before moving on that these terms, monochromatic, collimated, and coherent, are not absolute. There is no perfection here. To get perfect coherence, the pinhole would have to have 0 size. But if I have 0 size, then there is no light. So there are trade-offs, compromises. Therefore, perhaps one should put quotes at the end here on coherent, collimated, and monochromatic light. Another example of actually a device that is commonly used in many labs is shown here. That's monochromator. This device manipulates light, converting polychromatic light to monochromatic light. The polychromatic light from the light source is first collimated, then led to pass through a prism which refracts the light, i.e. different wavelengths are spatially separated or move in different directions after passing the prism, or it could be a diffraction grating as well. The focusing lens then focuses the different wavelengths in different parts, spatial parts, and the exit slit can then select a wavelength of interest. Another example of shaping light is wavefront shaping. This is a device with a long name, liquid crystal on silicon spatial light modulator, or LCOS SLM. It consists of pixels. So one pixel, each pixel has 2 electrodes at the bottom, shown in violet, and the top, shown in gray. Between the electrodes, you have a liquid crystal whose index of refraction can be changed by applied voltage. Different voltages can be applied to different pixels. And so, for example, when I have incoming wavefront, like plane wave, as it penetrates the LCOS, different indices of refraction will then retard some parts of the wavefront, i.e. changing its shape. So this device can be used to alter the shape of the wavefront. So earlier we said that nothing is perfect, and so for example, if I have a plane wave impinging on the lens, since lens is not a perfect device, it will not give me quote-unquote perfect focus. I can improve on the quality of this focus by, for example, using LCOS and reshaping or correcting the shape of the wavefront so that a better focus is achieved. These LCOS devices are commonly used in light squeezers where a sharp focus is needed to move, for example, cells up and down using light. Another example of manipulating light of great interest, actually recently due to application in automotive LiDAR, is MEMS mirror. It is simply a mirror whose orientation can be changed in 2 directions, as a matter of fact, 1 or 2, using a combination of electric and magnetic fields. So one can direct pulses of light or beams of light in desired directions. On the right-hand side, we see a plot, artist's conception, where the tilt angle by which this mirror can tilt is a function of driving frequency. Please note that the largest tilt we can get at the resonance. This mirror can be operated at resonance or away from resonance. The resonance frequency will be a function of the mirror, for example, its mass, its size, and its rigidity. And so here, just note that Hamamatsu, again, which sponsors this presentation, makes a wavefront shaper shown here. And on the right-hand side, we see some realistic images of how it can improve the quality of the focus. And another example from Hamamatsu are the MEMS mirrors in 1 dimension and 2 dimension. And I would like to draw your attention to the plot on the right-hand side, which shows optical deflection angle as a function of, in this case, the drive current, since these mirrors are driven magnetically. And that gives you an idea by what angle one can tilt these mirrors. Okay, so now equipped with some basic knowledge of light and light sources, let's discuss a variety of light sources. This will not be an exhaustive overview. However, I picked some common standard and maybe not so standard sources. We will not have any deep dive in any of them. However, I would like to mention that we are planning to offer webinars in the future that will focus on some specific light sources with a greater discussion, as we would say, greater deep dive. So it is, I think, mandatory to start with a black body, which is example of a thermal source. So here on left we have a black body, which happens to be a sphere of radius r, and area A, and temperature T. On the right-hand side, we see the spectral radiance, which we learned on the first slide, and the resulting shape is known as the black body distribution or Planck's distribution with the equation given above. One interesting feature of this distribution is that there is a wavelength lambda max at which the spectral radiance is maximum. One can show via Wien's law that this lambda max is only a function of temperature, goes as inverse of temperature. If I were to integrate the Planck's distribution over all wavelengths and the area of the black body, I would get total power, total radiant power emitted, and that is the familiar Stefan Boltzmann law. Please note that the power emitted is a strong function of temperature, goes as T to the fourth power. So even though a black body is idealization, in reality, in real life, there are no perfect black bodies, but there are objects whose emission can be actually quite well approximated by black body model. Sun actually is example of such body. Most stars emit approximately as black bodies. However, if I take a tungsten wire and put it into a glass enclosure, either in vacuum or with some inert gas, and raise the temperature, the resulting spectrum that we see on the right-hand side is looking quite similar to a black body. These illuminators, these quartz halogen tungsten filaments have many applications listed below. One advantage of these sources is that the light produced can look similar to solar light, and therefore they are used for general illumination, like in movie theaters and other places. Please note that by varying temperature, I can have peak emission in different parts of electromagnetic spectrum, like, for example, IR. And so this is example of black body source in IR made of graphene. So on left-hand side, we see the spectrum. These absorption features are simply due to surrounding gas. These sources are small and can actually be pulsed. Pulsing black body can be difficult because you have to change temperature, but the plot on the right-hand side gives you an idea of the time scales that one can have them pulsed. And so an important application of these sources, I will quickly mention, is IR spectroscopy. For example, the Fourier transform infrared spectroscopy. Let us now discuss another class of sources. These are discharge tubes. Here the basic design is as follows. We have a glass enclosure with two electrodes connected to a source of current, and in between the electrodes I can ignite plasma, shown with this red spark. It is that region, this plasma region, where light emission is produced. There are basically two processes by which you can produce light. One is excitation of electrons from lower energy states to higher, and then subsequent decay back. These processes, these transitions are going to give you discrete photons, or photons with discrete wavelengths. So that produces emission spectrum. However, electrons can also be excited to continuum. That causes ionization, i.e. that's how plasma is formed. And then the decay from continuum to energy discrete level does not produce discrete photons. You can get continuum which means a continuum spectrum of light. And therefore, the resulting spectrum seen on the right-hand side is a superposition of some continuum and discrete emission spectrum. There are many plasma discharge tubes. They differ depending on what gas is present inside. It could be deuterium, could be helium, could be neon, could be mercury vapor, sodium vapor, and others. Here's a quick table, which I will not read, but it's for your information, which shows some properties for three particular examples of lamps. And so here we see some items that we discussed before, like stability. Another one which I didn't, which is lifetime. Anyway, we have features and applications. So speaking about stability, these discharge tubes can have some stability issues. As the tube ages, the electrodes can corrode, and therefore the plasma arc that extends from one electrode to another can become unstable, i.e. its geometry or its configuration can change, can flicker. And so therefore that is going to lead to flickering of light or rapid, or maybe not so rapid, variation in the brightness. And so that is additional noise that the light source contributes into one's experiment. It is very difficult, in fact, nearly impossible to kind of clean those electrodes since they are enclosed, so with difficult access. And so remarkably, quite recently, a new type of light source has been developed. We call it laser-driven light source. This is actually a system that consists of a discharge tube where we initially ignite the plasma with electrodes, but then subsequently a laser, could be continuous wave, could be even pulse, a variety of lasers can be used. But anyway, the point is that it's the laser's light focused in between the electrodes that then sustains the plasma. So there are two effects of doing this. One is the plasma region is now as small as the focal point of the laser's light. And second is that the plasma region is not in contact with electrodes anymore. And so the plasma region became small and can be quite luminous. Both are great advantages. So let me briefly discuss the advantage of having small emission size. If I have a point-like emission, then I can capture the light with the collecting lens, collimate it, and then focus it again, perhaps so that this light can then be fed into a fiber for further processing. However, if the source is extended, it is in fact impossible to focus the light at the input of the fiber. And so what we are going to gain with a smaller point-like source is higher throughput and efficiency in transporting light from the light source to the subsequent parts of our optical setup. And so here's an example of such laser-driven light source from Hamamatsu, and one possible application to test photodetectors. So the light source produces stable, right? The key here is stable light, which is then expanded over some area, and there in that region I can place assembly, for example, photodetectors like CCDs or PMTs, and perform optical characterization. Now, an X-ray tube perhaps is not the thermal source, but I had a hard time kind of thinking where it should be put, so it is here. So let's spend a few minutes discussing X-ray tubes. As the name indicates, it's also a tube. It's kind of like a discharge tube, previously discussed. Here we have a cathode, which is heated to high enough temperature so that electrons evaporate from the cathode. They are injected into high field region and accelerated towards the anode. they strike the anode and suddenly deaccelerate or slow down, and we have to conserve energy. And so therefore, the energy of motion will be emitted, or some part of it will be emitted in the form of electromagnetic radiation. So in the lower right corner, we see the resulting spectrum. We can see on the x-axis is wavelength. Sometimes we can plot energy, but here it's wavelength. And so we see a broad distribution. However, there is the shortest wavelength, highest energy, lambda min. And that lambda min will depend on the accelerating voltage. At the top of the slide, we see examples of X-ray tubes from Hamamatsu. And you can see that the accelerating voltage are on the order of even hundreds, multiple hundreds of thousands of volts. Needless to say, X-ray sources are widely used in medical imaging. All of us went to a dentist once at some point in the past, and we took advantage of these tubes there by having X-ray performed. So now let's move on to some more esoteric sources of light. So let me spend some time discussing a supercontinuum. Supercontinuum is a situation that started kind of like an academic curiosity, but evolved into industrially applicable source of light. So what's happening? So suppose I have a pulse of light produced maybe by a laser, and I let this pulse propagate through what's called a nonlinear optical fiber. Though at the very beginning, physicists would project the pulse, let's say, at the glass, wine glass, and they would observe that the resulting spectrum of light is different from what was projected. So here, to be a little bit more formal, we are going to get this optical fiber. The nonlinear effect means that the optical effect taking place may not be proportional just to E, but maybe to E squared or B squared. Right? So these are effects that we do not normally learn in optics courses at the undergraduate level. They'll be taught in specialized graduate courses. So, long story short, the spectrum that we get out of the fiber is very different from what we put in. You can see below a spectrum which is very broad and spanning from about 400 to infrared, which was produced from a single femtosecond nearly monochromatic laser. So, as we said earlier, this was kind of curiosity, but with development of photonic crystal fibers, we can now standardize these sources. We can have repeatable pulses, repeatable spectrum, repeatable time characteristics, and thus they became practical. So if I have a fiber of certain length, as shown here, the PCF, and I inject a pulse with certain temporal and certain temporal characteristic and certain spectrum, as shown on the left-hand side, as this pulse propagates, both characteristics evolve with length, and therefore what exits the fiber depends on its length. So therefore, the output spectrum, the output time characteristic, the output coherence depends effectively on the length of the fiber. What kind of spectra can we get from the supercontinuum? This is an interesting plot from Physics Today, which shows the horizontal lines show the resulting spectrum of supercontinuum light if excited by wavelengths which are represented by the circles, and these circles represent various lasers. Anyway, the point is that some of these spectra span from visible to actually deep infrared. So really broad spectra can be produced. And on this slide, needless to say, is an example of supercontinuum source by Hamamatsu. It basically consists of a laser. This box is a laser and attached fiber. And below you have some technical characteristics which are very hard to read because of the small size, but the plot on the right-hand side shows the relative irradiance, effectively spectrum, of this particular supercontinuum source. Examples: turns out that broad sources with finite spatial coherence are of great interest in this application known as optical coherence tomography. We do not have much time to describe the details, but this is sort of like a Michelson-Morley interferometer in spirit, and it's used to map intricate biological structures, for example, in a human or other eye. So let's now discuss another set of sources which rely on solid state, and first, in particular, on the presence of p-n junction. And so p-n junction is a diode. However, if this diode is made of direct bandgap semiconductor, so I'd like to point out that silicon is not a direct bandgap semiconductor, but there are other semiconductors that are direct. The important difference is that when electron recombines with a hole, then light, photon, is emitted. And so if I take this diode, which is made of direct bandgap semiconductor, and I forward bias it, current begins to flow, and primarily in the depletion region, you have recombination of electrons and holes producing light. And thus we have light emitting diode or LED. This plot shows the spectrum. Expected spectrum is shown in red with a cutoff, and that cutoff would be determined by the bandgap energy. Turns out that the real LED does not really follow the theoretical spectrum. It kind of has a Gaussian-like bandwidth. However, the light is quite monochromatic, right? With the full half max ranging on the order of, well, depends on the semiconductor, depending on the construction, but can be nanometers to tens of nanometers. LEDs are all around us. There's an entire universe of LEDs, so I'm not going to spend much time, perhaps just showing you how they look, a portrait of LEDs, and some of the characteristics. The light that you can get can range from UV to IR, and actually it is also possible to construct LEDs that emit white light. I will not discuss how it's done, but it can be done, and so therefore there is a recent interest in using LEDs for general illumination. However, this was a little bit, not much was said about LEDs, so I could not resist discussing modulation of LED, because it is common error in the lab to try to modulate LED sinusoidally using the circuit above, where we have some DC voltage to activate LED, and then floating voltage source, sinusoidal, hoping that we get sinusoidally varying power. You will not get that, because power from LED is approximately linearly proportionally to current, but current for LED is not linearly proportional to voltage, and so therefore you are going to get distorted sinusoid. A better approach is to use floating current source to actually circuit the entire devices constructed and available in the market to sinusoidally modulate LEDs. So it is now time to discuss lasers, probably the most widely used system, because laser is really a system to emitting light. And so lasers are different from all the sources that we've discussed before. And so let me begin by discussing some basic requirements for a light source to be a laser. So first of all, we are going to utilize electrons, and therefore we have to have a material which is referred to as the gain material, that has at least two energy levels. And that's simple because there's, all materials have more than two energy levels. But these two energy levels will have to have some requirements, which I'm going to mention a little bit later, probably on the next slide. Second, we have to have a cavity, a resonant cavity, some sort of tube. It could be cylindrical, it could be rectangular, so resonant cavity. Third, we have to have mirrors at the end of the cavity. One mirror should be fully reflecting, and the other one partially reflecting or partially transmitting. It is on this end that light is going to emerge from the laser. Next, we need pumping mechanism. So there has to be some mechanism where electrons will be excited from the lower energy level to the higher energy level. This pumping mechanism could be electricity, could be light from a lamp, or could be light even from another laser. So there is not a single pumping mechanism, but a variety of them. And finally, you have to have ability of stimulated emission. So when electron is in the higher energy level, that energy level has to be stable enough so the electrons can hang around there for some time and be stimulated by the presence of photon to go to the lower energy level. So this is known as stimulated emission versus spontaneous emission, where electron will just go down without any kind of impetus. Because of the stimulated emission, the photons that are emitted are coherent, and so this is how a laser's light can acquire coherence. And if this pumping is maintained, in other words, as electrons go down, but I keep putting them back up, so I keep pumping, I can produce a stream of light emerging from the laser. That will be a continuous wave laser. Later, I'll discuss how we can get a pulse light from a laser. Let's now discuss a little bit more about the physics of laser. So I'll not repeat what we said on the previous slide, except point out that, yes, we have more than two energy levels involved, as shown on the left-hand side. Instead, I'd like to focus on the fact that the energy levels are not exactly discrete. They have width to them. That's due to Heisenberg uncertainty principle. And so therefore, if you have a transition from stage 2 to 1, you do not produce one single wavelength, but some distribution of them. And so this will be the distribution, or the spectrum, you could say, of wavelengths that can result from, in this case, 2 to 1 transition. As we'll see on this slide, this gives rise to so-called line width. I should note that there are other reasons for line width, which I'll not discuss in this presentation, only focus on this one. And so here, this slide gives you an idea of the line widths for various lasers. They can range from narrow, like 2 × 10⁹, to quite broad, 10 to 5 larger, like for titanium sapphire laser. So let's now look more closely at the cavity. And on the right-hand side, we have the line width for a given gain medium. The question is, what wavelengths are actually going to be present in this laser? And the answer is not all of them, but only those that satisfy the boundary conditions. So remember, light is electromagnetic wave, and so it has to satisfy certain boundary conditions. And you have two of those actually, longitudinal with the mirrors, but you also have tangential, which are not shown. But remember, this is some sort of tube, some kind of resonant cavity. And so therefore, there will be only a certain selection of modes, i.e. wavelengths, that can be sustained in the cavity. So for this particular laser, I would have, well, let's count, 1, 2, 3, 4, 5, 6, 7 wavelengths that can potentially be emitted. If I don't want all of them to be emitted, I might use some filters to filter out some of the modes. Please note that the separation between the modes in frequency, as the equation shows below, is inversely proportional to the length of the cavity. So the length of the cavity has great impact on the property of light of the laser. The term mode has a little bit of murky meaning in the world of lasers because it can also refer to the illumination pattern that the light produces. So this is an example of TEM modes for cylindrical cavity. These will be different, say, if the cavity is square or rectangular. And so probably the most common mode is the 0-0 mode, or the beam is Gaussian. However, you could have other modes, and you can see drastically different illumination pattern. One annoying feature of some lasers is if they hop between the modes, if there is instability. So you want Gaussian mode, but this laser can switch to some other modes. And so that can be, if not desired, a nuisance and source of errors. So let's now look at quickly at some lasers, actual lasers. So here on the left-hand side is the energy diagram of probably one of the first lasers, probably the most well-known laser, the helium neon gas laser. The pumping is achieved electrically by helium atoms colliding with neon atoms. So the electrons get excited, and then they undergo the lensing transition. On the right-hand side, you see the cartoon version of the structure, and so we have all the elements that we discussed earlier. We have mirrors, we have a cavity, we have a voltage source which provides the pumping mechanism. Now, we talked about LED, a PN junction. However, one can also make laser out of the PN junction. And so these are very common, popular laser diodes. So yes, we have to have resonant cavity, and we do. So at the junction between P and N, this purple region is the cavity. And yes, there are mirrors at the end which are required. So the inversion here is achieved by biasing, by injecting current, so that you have overpopulation of electrons in the conduction band, and likewise large population of holes in the valence band. And so electron goes down, recombines with a hole, producing a photon, but that photon will stimulate subsequent electrons to do the same. Of course, they replenish the electrons by continuing injection of current. And so the lasing action is taking place. There's a common misconception that light from the laser has to be collimated. No, it doesn't. Light still obeys laws of physics. This exit pupil is very narrow, so there is diffraction, which means that the light is going to spread out. If you want collimated light, you need to use lenses. Similarly, there's a misconception that light from laser has to be polarized. Well, it does not have to be polarized unless you polarize it. However, light from laser can have a large degree of coherence, temporal coherence, and spatial coherence, and that will depend, again, on how many modes the light laser produces. If I have a single mode, a single wavelength, then the temporal coherence is going to be very large, even hundreds of kilometers. Such lasers are of great interest in another type of automotive LiDAR, the FMCW LiDAR. Okay, so on the previous slide, we saw emission of light, which was in, I could say, horizontal direction. However, it is also possible to construct a PN junction laser, laser diode, where the emission of light is perpendicular to the PN junction. So these are known as VCSELs. This is actually a great reference to read about these devices, the history, and how they work. They have many advantages, desirable properties, I'm just going to mention one due to shortness of time, which is that you can have many such VCSELs produced on a single wafer. And thus you can produce what we call structured light. You can have structured illumination, right? From a single wafer. There can be thousands of such dots present. And again, this has interesting possible applications in a type of, again, automotive LiDAR. Again, I'm stuck on automotive LiDAR, which is known as the flash LiDAR. So a short break to advertise some of the laser diodes by Hamamatsu. We have a variety of laser diodes. This is just one random example of a possible choice. And on the bottom, you see some relevant characteristics of this particular device. Another type of very interesting laser, and something that you may want to focus in the future webinars, is the quantum cascade laser. This is not a PN junction device. I guess you could call it solid state device. It consists of narrow, what we call quantum wells. And so these materials like aluminum arsenide, gallium arsenide, there's a repeated pattern of them, right? Quantum wells. And these materials have different band gap energies. For this particular choice, 3 EV, 1.5 EV, etc. So we repeat this many times, tens of times. Now, if I apply a voltage across the structure, then this energy band diagram is going to tilt, as shown here. So on this slide, what we see, this is important to note, we see the tilted energy band diagram, but only showing conduction band. So the blue dot here is electron, and that electron is in the conduction band. And you can see that there are barriers separating the various wells. Okay? So electron in well N can tunnel, quantum mechanically tunnel through the barrier to well N+1. But because of applied voltage, the energy level, the first excited energy level, is actually below the ground state, E1, in well N. And so therefore that electron can then lace or go to the ground state, emitting a photon. And this can be repeated. This electron can again tunnel through to well N2+1/2 and emit a photon, i.e. can cascade through these wells, emitting multiple photons. So yes, we can have also cavity, we have mirrors, and one can construct the laser. Before moving on, I would like to point out that this slide is not a complete explanation of how this laser operates. This is the Kazarinoff series idea, which cannot be actually physically implemented. There has to be modification made. However, such modifications were successfully achieved, and successful quantum cascade lasers do exist, and Hamamatsu offers them as well. So here we see an example of QCL laser. These lasers have multiple advantages. One is that one can have emission in infrared, even deep infrared, and that will be predicated on the choice of the material. And second, these lasers are tunable, which means you can change the wavelength of emission either with injection current or temperature. And so before, we have only little time left, so before finishing this presentation, I would like to very quickly discuss some common terminology used in connection of lasers, and one of them is Q switching. So Q switching allows lasers to be pulsed. By Q, we mean quality of the cavity. If cavity is low, if Q is low, then there is a lot of absorption, and that means that no light can be sustained. So you don't have resonant mode. you can have inverted population, but no modes sustained. Now, if I can change the Q, and I'll show you later how we can do that. So I go from low Q to high Q, the quality of the cavity becomes high, and that means that it becomes resonant. And so that means that I can now have electromagnetic waves resonating in the cavity. Thus, I can have emission. And so switching between low Q and high Q allows you to produce pulsed emission. There are many ways, well, not many, there are a number of ways of varying Q. One of them is to use polarization. So the cavity will contain polarizing filter, and also apical cells whose polarization can also be changed using a voltage. And so therefore, the Q, or the changes in Q, can be simply achieved by changing the orientation of the polarization axis of this pair. So this kind of works like a polarizing filter, not filter, but cross filter, which allows you to vary intensity of light, a very common device in optical labs. So this is what we mean by Q switching. You can have a pulse emission. And the final concept I'd like to review briefly, very briefly, is femtosecond laser with the mode locking. So the duration of the pulse can be made very short, in fact, as short as femtosecond. To do that, we have to have many modes, because by Fourier-like thinking, these different modes represent different frequencies. If I combine them, I can then achieve a pulse in time domain that has a narrow duration. Right? So just remember from, say, circuit theory, if I have a delta signal in electrical signal, then if I perform Fourier transform of that, I'm going to get effectively an infinite number of frequencies I need to construct such pulse. So this is very similar here. I need many modes to construct a pulse of narrow duration. So now we can think of this pulse bouncing between the mirrors, but please remember one of the mirrors is partially transmitting, therefore the intensity of the pulse should decrease, therefore we should be able to energize this pulse. So pump energy into the pulse, and that's achieved by so-called mode locking using amplitude modulation, which is basically borrowed from radio physics. If I have, so remember our laser has many modes. These modes are separated by some frequency difference. We know that it's C over 2L. And so if I'm going to now modulate the Q of this laser with that frequency difference, what happens incredibly is that all the modes are going to be re-energized simultaneously at the same time. And so that's known as mode locking, and therefore I can sustain the power of the pulse. And to finish this topic, here's an example of a picosecond laser by Hamamatsu, and I would like to mention one important application, or again, time-of-flight LiDAR, automotive LiDAR. In one concept, would like a laser to produce short duration pulses, maybe not femtosecond, but under of nanoseconds, but would like these pulses to be with peak power of hundreds of watts and emission in IR. And on the right-hand side of the slide, you see a possible solution to this requirement offered by Hamamatsu. So we've reached the end of the presentation. I would like to leave you with the summary of light sources that Hamamatsu offers. Again, most of you, if not all of you, think of Hamamatsu as a photodetector company, and yes, we are, but we also make light sources as well. And you can see that the list is actually quite large. I would like to thank everyone for listening to this presentation, and until next time, thank you.
Thank you. Now we have a few polling questions we would like you to answer. Please participate in answering these 3 polling questions at the end. Your answers are important to us. We're going to give you a few seconds to answer the question. Okay, just another few seconds and we'll now send the results. Okay, now we're going to send you the second question and give you just a few seconds to answer. Okay, just another few seconds and we'll send the results. And now we're going to send you the third question and give you a few more seconds to answer. Okay, just another few seconds and we'll send the results. And before we wrap up today, just a reminder that today's presenters have made available a PDF of the presentation, as well as a brochure on photonics devices. You can download those assets by clicking on the Event Resources tab just under the Ask a Question box. I'd like to thank today's presenter, Slavomir Pajatek, Science Consultant for Hamamatsu, as well as our sponsor, Hamamatsu. And I would like to remind you that the on-demand version of this webcast will be available on the Laser Focus World website within 24 hours of this live presentation. The link to the archived webcast will be sent to everyone who is registered for today's event via email as soon as it is available. On behalf of Hamamatsu and Laser Focus World, I'd like to thank you all for attending. Have a wonderful day.